Namaste and welcome to yet another lecture on linear algebra through geometry. We are in the process of understanding the idea of vector spaces and stuff. We looked at certain examples. I had taken the set of all vectors, let us say in R2, that means your 2 component set of all 2 component vectors. In the previous class we also looked at the example of set of real symmetric 2 by 2 matrices. We proved that that is also vector space. Of course, in the examples that I have considered, I had just taken those 3 properties, which is closure under addition, closure under scale multiplication, and the existence of the 0 vector. I would also suggest that all of you please work out the other properties, 7 properties, and ensure that in fact all those other 7 properties also hold good, and then say that look, this is indeed a vector space, right. So, that is the thing that we looked at. We also looked at another example wherein which we took the scalar multiples of a particular vector, let us say x1 into 1 1, that means the set of all those vectors where 2 component vectors where both the components were the same, and we also established that it is a vector space. Of course, again a word of caution, please ensure that you work out all the other 7 properties also, and ensure that obeys the set obeys the 7 other properties, and then come to a conclusion that it is actually a vector space, right. Yeah. Now, what we do is we are going to look at some more examples, and we look at these examples and try to kind of generalize again in terms of this geometry. We are trying to generalize certain interesting things as far as these vector spaces is concerned, and then what we do is we go into the idea of vector subspaces. So, that is the intention behind this lecture. So, what we do is we are going to look at some more examples of vector spaces, and then we are going to get into the idea of the vector subspaces. Okay. So, let us get going. Examples of vector spaces. So, in the previous lecture, before we get into this, so we defined the our vector space. V is a vector space. So, recall V is okay, any non-empty subset V, any non-empty set V, a non-empty collection V with plus and dot the rules for carrying out vector addition and scalar multiplication. Vector addition, basically carrying out rules for carrying out addition of 2 elements of V, let us put it that way, and then we put that element of V as vector. So, we will say carrying out addition of 2 elements of V and for multiplying let us say real scalar with the element of V respectively, and that which obeys, and that obeys, we had 10 properties, properties 1 to 10 listed before. One to 10 is called as a vector space. over R. This over R is essential because we are saying that okay, the components are all going to be real numbers and so on, and therefore the addition and other things that we say are basically how it is done in our real numbers, I mean addition of two real numbers and multiplication of real numbers. In fact, you can actually define your own rule for adding combining or adding two vectors, multiplying two vectors, that is also allowed. Okay. So, we have yeah, I mean in the vector space that is also allowed, right. So, space over R is called as a vector space over R. So, every element of a every element of V is called as a vector. Every element of V is called as a vector. Now, let us take some more examples so that we get a better understanding. Let us go to some more examples. What is the example that we are going to look at? We are going to say the set of, okay, let us take this V, which is basically of this type, let us say x1 to x1 in R, right. Here again I will do the first three properties. Please ensure that you do the rest of the properties and check whether it actually works out, check whether all the other properties hold good. So, this we will see that is a vector space. Maybe let us look at this example as a vector space. So, we will see that suppose U and V are elements of V, then this vector U is basically u1 comma 2 u1 and vector V is basically v1 comma 2 v1, and let us look at let alpha and beta be real scalars, then we have the first one. We are going to say u plus v, let us verify each of these properties. U plus v, which is nothing but u1 2 u1 plus v1 2 v1, which is nothing but u1 plus v1 2 u1 plus 2 v1, which is basically u1 plus v1 2 times u1 plus v1. That means the resultant vector is also having the second component to be 2 times the first component. So, we have this, that means we say that u plus v is therefore an element of V. So, closure under addition, vector addition, closed under vector addition, that works. Then let us take the scalar alpha a real scalar. We have already discussed that. So, what we are going to do is we are going to take alpha times the vector u, which is nothing but alpha into u1 to u1, this is nothing but alpha u1, then alpha into 2 u1. Since we know that if you multiply two real numbers, you can change the order of those two real numbers and yet the result is the same. So, you are going to have alpha u1 and 2 times alpha u1. So, which means this is also an element of V. Therefore, V is closed under scalar multiplication. V is closed under scalar multiplication then we want to check if the commutative property holds good. Let us look at the third property. We want to check if u plus v is the same as v plus u. So, we will take u is equal to u1 to u1 and v which is v1 to v1. So, we take u plus v is nothing but u1 plus v1 2 times u1 plus v1 and v plus u is this we have v1 plus u1 and you are going to have 2 times v1 plus u1 and a plus b are real numbers. When you add them you have this commutativity to hold good. So, this is the same as u plus v, therefore, it is closed, I mean the commutative property holds good. So, you can look at all these things. I am going to now look at the idea of okay, let us look at if distributivity, I mean associativity and other properties holds good. Let us take u, v and w. So, what are we going to have? We are going to say u plus v plus w, we are going to look at this which is basically u1 to u1 plus v plus w is nothing but v1 plus w1 2 times v1 plus w1 which is again I am going to use this vector addition. So, I am going to have u1 plus v1 plus w1 and then I am going to have 2 times u1 plus v1 plus w1. This is what I have. Now, I am going to look at u plus v plus w which is nothing but u1 plus v1 2 times u1 plus v1 plus w1 2 times w1. We can see that u plus v plus w is the same as u plus v plus w. This is because you have your real number addition, right, and we are going to look at the 0 vector, existence of 0 vector. So, let us look at this 0 comma 0, this is the next property which is basically the so that is basically the, so what did we do? Okay, so this is 1 2 scalar, this is done. So, I am to have the fourth property 0 comma 0. Let us see if this is actually there in that set. So, what are we going to do? We are going to say that for this vector, the 0 vector is basically this, you can write this as, we know that it is going to be this is nothing but I can write this as 0 2 into 0, therefore, this is also there in V, therefore, 0 vector is also present. You can list out all the other properties, please check other properties. We will see that this V, which is basically the set of all those points x1 to x1, set of all the scalar multiples of the vector 1 2 where x1 is a real number, is a vector space. Right. I am going to take one more example now. This is example 2. Let us just let us look at this vector space V which just contains the 0 vector. It just contains the 0 vector. Since it contains only 0 vector, all that you can do is you can add 0 vector with the 0 vector itself. So, the resultant is going to be 0 vector. You take any scalar alpha and then multiply with the 0 vector, you are going to get alpha into 0, that is going to be the 0 vector again. the set contains nothing other than the 0 vector, therefore the additive identity is also guaranteed. You can list out all the other properties and check that this V is also a vector space, is a vector space. Example 3. Okay. What we are going to do is we are going to look at this example 3, set of all diagonal matrices right with diagonal elements from R. So, let me call this set D, I will say diagonal 2 cross 2 or diagonal 2 cross 2 matrices, 2 by 2 diagonal matrices. This is what we are going to look at, which is going to be of the form D1 0 0 D2 D1 comma D2. We have told that these are elements from R. You can check that the set of diagonal matrices is indeed a vector space, is a vector space over R. Does the 0 matrix is the 0 matrix a diagonal matrix? Of course, we have D1 and D2 to be 0, it would still be a diagonal matrix. So, we will have that. Then if you add any two diagonal matrices, the resultant is also going to be a diagonal matrix. Scalar multiplication, that is also going to give you diagonal matrix. So, we will see that set of all diagonal matrices. These are some of the exercises which you can probably work out, and then they prove that indeed it is a vector space, right. Now, we are going to look at another example, example 4. Let us look at example 4. Let us say set of all polynomials, let us say polynomials of degree, let us say less than or equal to 2 with real coefficients, right. Okay. So, let us denote this, let the set be denoted as P2 of x. Okay. Let us just denote this set by P2. Now, what we want to do, therefore, P2, the polynomials in P2 will have this form. So, P2 set contains polynomials of the form P is equal to, let us say, P naught plus P1 x plus P2 x squared, right, P naught plus P1 x plus P2 x squared. This is what we are going to have. So, how do we check whether this is going to be a vector space or not? We need to look at all the other properties also. We will define the vector addition and the scalar multiplication to be the usual operations, like. So, we will check if P2 is a vector space under usual vector addition and scalar multiplication. So, let us try to solve this and then check, right. Let us look at this. So, first of all, closure under addition. So, what we do is we know how to add two polynomials. Say for example, I have two of those polynomials which are let us say AP is basically a polynomial of the form let us say A naught plus A1x plus A2x squared. Let me put this as that script P, and BP, let us say this is B naught plus B1x plus B2x squared. You can say AP plus BP is going to be of the form A naught plus B naught plus A1 plus B1x plus A2 plus B2 x squared, which is the same as the form that we had in P2. So, this is going to be closed under addition, right. So, we are going to say that sum of any two polynomials of degree less than or equal to 2 of degree less than or equal to 2 is also a polynomial of degree less than or equal to 2. Right, it is also a polynomial of degree less than or equal to 2. Then you can look at all this other properties like commutativity and okay, let us do scalar multiplication and stuff. Let us say scalar multiplication. Now, what is it to say scalar multiplication? Suppose I have let us say let alpha be a real number and let us say AP be equal to A naught plus A1x plus A2x squared. What we have is alpha times AP is nothing but alpha into A naught plus A1x plus A2x squared, which is nothing but alpha A naught plus alpha A1x plus alpha A2x squared, and that is again an element of our P2, right. So, this is also an element of P2. So, here this also we see is an element of P2. How about this 0 vector? That is also there, because I mean how about the 0 polynomial? Since we have said it is a polynomial of degree 2, that means you can actually have just a constant less than or equal to 2. We have said that means degree constant also can be there, which means you do not have this, the coefficients are all 0, in which case you are going to have the 0 vector also to be present, and therefore we say that verify other properties and establish P2 is a vector space. Now, there is something interesting here. What is that? The thing is, we have said clearly that it is of set of polynomials of degree less than or equal to 2. Suppose if I had put strictly polynomials of degree 2, then it is going to be a problem, because you may have two polynomials, let us say AP and BP, such that A naught plus AP is A naught plus A1x plus A2x square, and BP is B naught plus B1x minus A2x square, and when you add these two, x squared term gets knocked off, you will get a degree 1 polynomial, which will not be there the moment I say I am going to look at set of polynomials of degree strictly equal to 2. So, any set of polynomials of degree strictly equal to n will fail to be a vector space over real numbers, real coefficients, whereas a set of polynomials of degree less than or equal to n will be a vector space when the coefficients over real coefficients. So, we are going to have coefficients to be real, and you define your vector addition and scalar multiplication in the usual manner, it is going to be a vector space. So, it will happen only when you take degree less than or equal to n. Okay. Now, the third thing that we want to do is we want to look at let us say let us take this what is the example number, example 5. Example 5. What are we going to say? We are going to look at this set, basically a plane, let us say in R3 that passes through the origin. A plane passing through the origin in R3. So, how is it going to look like? I am going to have something like this. So, we are going to have this x1, x2, x3 axis. What are we going to say? Like I am going to have a vector, let us say, which is a1, or let us say this is the vector, let us say v, and let us look at another vector which is basically another vector which is let us say u. Now, these two are linearly independent vectors, therefore, that what we are going to have, you are going to have an entire plane to be formed by these two linearly independent vectors, and the vector u and v have their we are taking it with respect to the origin, the references with respect to the origin. So, let us see if this is basically a vector space. Okay. So, we basically say that the initial points of all vectors in R3 all vectors is at the origin. The initial point of all vectors in R3. R3 is basically your 3-dimensional space that we are going to look at. So, we want to see whether this is going to be a vector space or not. So, what does it mean? So, we are going to basically look at this. Let us take this. So, this is basically the plane that we are going to have, right. You can complete the parallelogram and stuff. So, you are going to have this to be the plane which is determined by those two vectors u and v, and what we are going to do is we are going to look at whether this is a vector space or not. Okay, so, how do we do that? So, the first thing is consider two vectors So, we will actually give the name for this plane. So, let us say let W be the plane passing through the origin in 3D, the origin in 3D. Yeah, we want to see whether if W is a vector space or not. Okay. So, let us look at let us take any two vectors. So, let U and V be any two vectors. Okay, we have taken this as U. Okay, be any two vectors. Maybe let us change this name. Let me make this so let me call this as the okay V vector, big deal. So, let us take x and y be any two vectors on the plane, right, on the plane. So, the moment we say it is a plane, the vectors are in the plane, the parallelogram formed by x and y is entirely in the plane. Let us take that is entirely in the plane. Right, it is entirely in the plane, and what we see is because x and y are in the plane, right, and x plus y, which is basically the diagonal of the parallelogram, is also in W. Therefore, we can say W is closed under vector addition. W is closed under vector addition, and no, the thing is like okay, scalar multiplication what do we mean by scalar multiplication? You take let alpha be any scalar and u be a vector on the plane, vector in W, right. So, what do we have? Alpha u is basically the scalar multiplier, it is basically either parallel to u, because the scalar multiple of the vector is basically either parallel to u or it is the 0 vector. Why? Because if you take alpha is equal to 0, naturally alpha into the 0 u vector is going to give me the 0 vector, and that 0 vector is there in the plane because we have actually taken the all the vectors that we have to be the what you call they have their I mean the initial point of all the vectors is basically there at the origin is what we have taken. So, therefore, this is going to be the 0 vector. So, alpha u is either parallel to u or is equal to the 0 vector. Therefore, what we say, since the plane passes through the origin, if alpha u is equal to the 0 vector, it is in W, and any vector which is parallel to u will also be an element of W, that means it is closed under your scalar multiplication. We can actually look at all the other properties, we can see that the rest of the properties also hold good. Properties hold good. Therefore, any plane passing through the origin is a in R3 is a vector space. Right. So, what we have done now in this lecture is like we looked at some examples of vector spaces, I mean which included certain interesting things, that we looked at a set of polynomials of degree less than or equal to n. We just looked at the singleton 0 vector, which again was a vector space. The set of polynomials of degree less than or equal to n was also a vector space, that is what we saw. Then we saw that any plane passing through the origin in 3 dimension is also a vector space, that is also something which we saw. Now, why are we doing all these things, like what is the I mean where are we heading to with all these things? We will see sometime in the next module when we look at the system of equations and solution to system of equations. We will look at all these things that we have done now in terms of the the plane passing through the origin. In fact, if you look at this set of vectors, which is basically of the form x1 comma 2 x1 that we did, this is basically a line passing through the origin in 2D. So, what we have seen is we are basically seeing a line passing through the origin is a vector space, be it in 2D or 3D. A plane passing through the origin is a vector space in 3D, right, and therefore, what we see is we see the geometry of these vector spaces coming into picture, right. We see that. So, let us make a general comment here. We see that any line passing through the origin is a vector space the origin is a vector space any plane passing through the origin is also a vector space. Is a vector space. So, this is also something we saw. So, now what we are going to do going ahead from here, we are going to look at the definition of vector subspaces, and then we are going to look at the idea of combining vectors in these vector spaces and vector subspaces, where we are going to look at linear combination and linear independence, followed by what is called as the basis for a vector space and subspace, and followed by the dimension of a vector space. So, in this lecture what we have done is we basically looked at some examples of vector spaces. In the next lecture we will look at subspaces. When does a set qualify to be a vector subspace? That means the moment I say subspace, it conveys something similar, a meaning which is something similar to a subset. So, which means I am going to look at subset of a vector space. So, when does a subset of a vector space qualify to be a vector space, means subspace? And what we are going to do is we are going to look at, again the next one we are going to look at is combining vectors in terms of we are going to look at the linear combination of vectors, linear independence and basis and so on. So, that will be the agenda for the next lecture. Thank you.